In March of 1991, the Lawrence Livermore National Laboratory evaluated a mine countermeasure device.
A helicopter-towed system would have three advantages over a conventional ground-based system for discovering and clearing mines. First, it has the ability to deploy the device at a distance in a short time. Second, it has the potential to sweep large areas rapidly. And finally, it has the ability to work over shallow water as well as land. The first mine countermeasure design was a chain matrix assembly that consisted of a front portion of digging knives and a rear assembly of blanket harrows, augmented with chains to add extra weight and stability. Inexpensive modular devices, digging knives, were designed to dig up, dislodge, or detonate mines. The knives are mounted in a row so that even if several are destroyed, the chain matrix can still function as a minesweeper. As an effective minesweeping drag, it could be trolled at the end of a long line, yet not be completely destroyed by the first large blast it encounters. Early tests at Livermore showed that a chain-link system, such as this one, can survive many detonations that would destroy more rigid structures. The digging knives are stable when pulled, unlike many manual minesweeping devices that are easily trapped by rocks and other ground-level obstructions. In the role of mine detection and clearing, this design may have the potential for sweeping large open terrain, such as desert or beach areas, more rapidly than other mine countermeasures. It may also prove effective against tilt rod and other similar mechanically activated mines. Tests were conducted at the U.S. Army Proving Grounds in Yuma, Arizona. The desert terrain on this site is nearly identical to that found in Iraq and Kuwait. Both performance tests and survivability tests were conducted. Prior to this, load tests had been conducted on both the chain matrix and the rake devices to establish draft requirements in that desert soil. As currently designed, the chain matrix system can be pulled with approximately 25,000 pounds of drawbar force. Our tests used a half-width model of the chain matrix, requiring only 12,500 pounds of drawbar force. For the performance tests, a mine field containing 36 anti-tank mines, half of them plastic and half of them metal, were laid out at varying depths according to Soviet doctrine under the guidance of the U.S. Army Waterways Experiment Station personnel. As a first test of this concept, and because a suitable helicopter was not available, an M60 tank with a 500-foot cable pulled the devices across the field. In the first 4 tests, the chain matrix was pulled across swaths of mines buried half an inch, 2 inches, 4 inches, and 6 inches deep, respectively. The depth was measured to the tops of the mines. Since these were real U.S. inventory mines, we established strict safety procedures. Observers were located behind blast protection. Remote cameras were set up to record the tests. Between each test, explosives ordnance disposal personnel ensured that the chain matrix was clear of mines as it was lifted by a crane and repositioned for the next test. The chain matrix clearly demonstrated an ability to encounter and remove mines buried at depths ranging from half an inch to 6 inches. Many of the mines were removed completely. Of those that remained in the ground, a high percentage showed evidence of having been contacted or moved. In the 6th test, the chain matrix assembly was towed across a field containing 15 anti-personnel mines buried with their top surfaces just covered. We performed 3 survivability tests on the chain matrix, 2 of which were conducted while the device was under dynamic loading. An anti-tank mine with detonation cord attached was buried at a depth of 12 inches, deep enough to preclude contact by the digging knives and harrows. An electrical initiation system was used to command detonate the mine at the desired time. In the first two tests, the chain matrix was being pulled over the mine. In the third test, the chain matrix remained stationary, and the mine was detonated against the digging knife in the forward section. A 10-pound explosive mine destroyed only 1% of the effective working area of the chain matrix as designed. A 20-pound explosive mine destroyed only 10% of the chain drag. At this point, we believe the basic capabilities of towed mine countermeasures have been successfully demonstrated.
This is a film of a field test of the chain matrix helicopter mine sweeping system developed by Dr. Bill Wattenburg and the Lawrence Livermore National Laboratory. This test was conducted on the 7th of May, 1991, near Riley, Oregon. This specially equipped Vertol 1072 helicopter was supplied by Columbia Helicopters of Portland, Oregon. This mine-sweeping chain matrix was previously tested over actual mine fields at the U.S. Army Yuma Proving Grounds. It was delivered here by Lawrence Livermore personnel. The chain matrix was designed so that it can be transported like a roll of carpet and then rolled out by hand. The three main components, the chain blanket, the anti-snag digging knife units, and the drawbars, can be assembled by hand in less than an hour. The entire matrix weighs just 4,000 pounds. Here you see the helicopter's 400-foot-long line being attached to the chain matrix. Columbia's experienced pilots and ground crews perform this task hundreds of times every day on their heavy-lift logging and construction jobs. This ship and crew just finished a nearby logging job. The pilot straightens out the matrix, orients it in the pulling direction, and begins to sweep a 1-mile oval path around this field. You can see the digging knife units in the center of the matrix immediately engage the ground. The dirt plowed up rolls over them like a wave of water, and it is then smoothed out by the chain blanket behind. As part of this test, the helicopter is now going to drag the chain matrix at high speed over a rough terrain area that is rocky and covered with brush to test the anti-snag characteristics of the digging knives. The helicopter is now pulling the chain matrix at over 20 miles an hour through this rocky terrain. The pulling force never exceeded 10,000 pounds, less than half the capacity of Columbia's largest helicopters. Now the helicopter executes a second 90-degree turn. The pile of dirt you see here is actually a moving wave of dirt as it boils up behind the digging knives, which are penetrating 6 to 8 inches in the ground. The ground speed here is 12 miles per hour. We've buried several simulated mines along this path, which are 12-inch diameter concrete patio discs, as you'll see later. The chain matrix is now being inspected at the end of the 1-mile run. As you can see, the digging knives and the matrix dug up or captured just about every solid object larger than 4 inches in diameter. Here is one of the concrete discs that had been buried. The path swept over by the chain matrix is now soft dirt to a depth of 6 inches.